Okay, well, welcome back, everybody. So in this video lecture on introductory econometrics, we're going to be learning about the topic of heteroskedasticity. Now, this is a particular type of problem that we run into in regression analysis. It's quite common. We will be learning in this video about how to identify it, what the consequences of it are, what it is. I guess I should have said that first. How we test for it, and then how we potentially remedy it. Now, in discussing heteroskedasticity, we should first differentiate between so-called pure heteroskedasticity and impure heteroskedasticity. Pure heteroskedasticity, which is much less common, occurs when a variation in the error term is not constant in the correctly specified model. Okay. So in that, it's similar to our problems of perfect multicollinearity and perfect serial correlation that we've discussed already. Impure heteroskedasticity occurs when there is a variation of the error term associated with a specification error. So a specification error in the estimated equation. All right. So first of all, what is then heteroskedasticity? Well, heteroskedasticity occurs when we have a variation in the error term correlated with the value of one of the independent variables. So in that sense, it's very similar to the concept of autocorrelation, which we studied in the last video. Autocorrelation, you'll recall, was when observations of the error term were correlated with other observations of the error term. Okay. Heteroskedasticity is where observations of the error term are correlated with the specific value of one of your independent variables. Okay, so let's say that, to give you a quick example of that, let's say we had a variable like age, right, and that we were regressing that against income, right? So how does a person's age explains one's income? Well, it's likely that when people are 3 or 4 years old, their incomes don't vary very much. Right? Little kids don't really have much income. Maybe they got $10 at their birthday or something like that. But they don't vary much at all. But of course, as people age, they take different paths in life, and the variation in incomes across a set of individuals at any given age is very likely to increase significantly. Okay, this is the problem of heteroskedasticity. Now, to determine whether we're observing heteroskedasticity, or whether heteroskedasticity is occurring in our estimated equation, a straightforward and simple thing to start with but not conclude with, is to plot the residuals. Okay, and if you see something like this over here, chances are pretty good that you have heteroskedasticity in the estimated equation. Now, here we see heteroskedasticity illustrated as a sort of fan shape that is expanding as x or y increases. But it needn't be so. It needn't be this way. It could be that the variance in the errors first expands and then contracts, right? So it could be sort of a something caught in a snake sort of pattern too, where we've got skinny and then a big bulge and then back, right? So if we go back to our example from a few minutes ago, if we can imagine that at something occurred, actually maybe it does occur like that. Maybe so variances in incomes as people age expands, right, as they enter in their working age. As they move into retirement, their income's likely, the variances in their income contract back down. So you have something that looks like this, and that's still going to be there's still going to be heteroskedasticity introduced into your estimated regression equation. Okay, so it can take a variety of forms. It's critical to understand that what's going on. It is that you're getting your error term variances in your error term being correlated with the value of one of your, or more than one of your independent variables. As one would expect, heteroskedasticity ends up occurring most frequently when you have large variations in the observation of your dependent variable as well. Okay, so this is going to happen quite frequently. So let's say you're looking at something like incomes or home prices, something like that. The variation between your lowest price and your highest price, or your lowest income and your highest income, are going to be quite extreme, and that is more likely than not, going to introduce heteroskedasticity into your estimated regression equation. Heteroskedasticity can also result from outliers in the data. So when you have observations that are far divergent from the bulk of your observations, right, it can introduce heteroskedasticity. It can also result from the incorrect functional form, right, as you might anticipate, and a variety of other things, right. So it's not uncommon at all to have some heteroskedasticity in your estimated regression equation. So don't freak out when it happens. Okay, some of the consequences then of heteroskedasticity are very similar to what we saw last time with autocorrelation, again, because sort of the nature of the problem is very similar. Pure heteroskedasticity does not cause bias in your coefficient estimators. So if you as long as the equation is correctly specified, the presence of heteroskedasticity alone does not mean that your estimated betas are biased in one way, shape, or form. Okay, but it does mean that OLS as a method is no longer going to be a minimum variance estimator. That is to say, it's no longer BLUE, or a best linear unbiased estimator. What's going to happen is, when you have heteroskedasticity in your estimated regression equation, is your standard errors associated with your estimators is going to be biased, right? So essentially, you can't rely on your estimators as well as you would be able to do otherwise. And as a consequence of that, as you might imagine, your T and F tests associated with those estimators are also not necessarily going to be very reliable. Okay, so now that we understand sort of what heteroskedasticity does, or what it is, and what it does to our estimated regression equation, how do we see whether we have it? Okay, there are way more tests for heteroskedasticity than I'm going to go through here. These are, again, as I've said before, these some of the bread and butter tests that a lot of statistical packages have embedded within them. So oftentimes it's simply a matter of point and click to run these tests. But there are many other tests for specific types of heteroskedasticity or specific problems that you're encountering with your model that might be more applicable. So a literature search would be well considered to see what other folks have done. But the first of these is this Breusch-Pagan test. And how we run that test is we're going to obtain the residuals from the estimated regression in this manner. Okay, and again, I'm going to go through this quickly because we just discussed this in the last video. So on serial correlation. So if you're watching this and you're like, oh, slow down on that. Okay, well, go back and watch my video on serial correlation, and we talk about it in a little more depth there. Okay, from that, we're going to use the squared residuals as a dependent variable. So we're going to take the square of what we get in the first one, right, plop it down into the auxiliary regression below that, and then we're going to test that equation for significance using a chi-squared table, and particularly the test statistic is going to be nr squared, or the number of observations n times the r squared associated with the estimated auxiliary question. Okay, and so what we're looking for there is that alpha 1 equals alpha 2 equals 0. Okay, the second test, and I'm going to say maybe even the most common, a bit more common than the last one, is the White test, at least in my experience, right? The White test. So obtain the residuals from the estimator, so same as before, right? And then you're going to estimate the equation using the squared residuals as a dependent variable, using each x, the square of each x, and the product of all x's. Okay, so let's grab the mouse here, which I don't like to do for some reasons, but okay, so the square of the estimated residuals, right? Alpha 0, so we're going to employ an intercept coefficient. x1 and x2. So we're working from an equation that just had two independent variables initially. If you had three independent variables, right, then you would have x1, x2, x3, and so on and so forth. Then you're going to take the square of each of those. Okay, so square here of x1, the square of x2. Again, if you had x3, you'd also have the square of x3. Okay, and x4, and so on and so forth. So you can see if you're talking with an estimated equation with 30 or 40 variables, doing this by hand is going to be quite arduous. Okay. Finally, then, the x1 times x2, and again, if we had x3, it would be x1 times x2 times x3. Okay, that product as the final component of our estimated equation. We are then going to take the r squared associated with that, multiplied by the number of observations in our sample, and we're going to test for significance using a chi-square table to determine whether we have heteroskedasticity according to the White test. Okay, so let's say you've run one or both of those tests and it turns out you have heteroskedasticity. What are you going to do about it? Well, there are many remedies for heteroskedasticity, and so one should first of all consult the literature to see what other work has been done regarding the specific nature of the heteroskedasticity you are experiencing. But in terms of very sort of bread and butter approaches, if you have if you believe the model is correctly specified, meaning that you have pure heteroskedasticity, using a WLS or a weighted least squares approach in a manner similar to what we outlined last time in the serial correlation video would be a reasonable approach. If you believe that the model is perhaps not correctly specified, which is often the case, then you want to start looking for omitted or improper variables, incorrect functional forms, right? False associated with the underlying theory. Okay, in other words, maybe your model just has the economic theory wrong as well. Okay, we've discussed the problem of omitted variables or improper variables in a separate video at this point, and how we would sort of look for that and what signs we would be looking for. Right. So in that case, heteroskedasticity is going to accompany one of those other problems that we may have observed. We also have a separate video on choosing the correct functional form. So we've discussed what some of the signs of trouble there look like, as well as the remedies. Okay, so this problem of heteroskedasticity can certainly accompany or can be indicative of one of those other problems that we've already discussed. That's it for this time. I think this one was pretty short, but that's good because we're getting pretty far into our work here. This is our last lecture on our sort of problems, sort of standard problems associated with regression analysis. And next time we'll be sort of starting the final section of our lectures on various extensions of regression analysis. And the next one, as you noted over there, being time series models. I hope you'll join me there, and I'm really enjoying this series. And always there are companion videos to associated with this, where I actually show you, using the eViews software, how to run these tests, check for these things, like check for omitted variables, functional form, all this kind of stuff. So please have a look at those as well if they can be useful to you. Thanks everybody. Have a good day. See you next time.